Okay, so we are going to have to rely on some technology, okay? And logs is not about using a calculator, okay? But when we don't have common bases, we are going to have to rely on some technology. We can use our calculators for that eventually with logs as well. But before I introduce logs, really we just need to use technology. We need something to calculate this for us. So we can use a graphing calculator. We can graph this. So this is one strategy we already have. So if I want to solve this equation here, and I have this base 3 here, and my 60 and 2, they can't be expressed with base 3s, even if we mess around with this. So what we can do is we can graph this equation, make it equal to 0, graph, and I can solve the solution. So the exponent here is my unknown, and I can find that exponent by graphing it. And the graph, in some ways, is the calculator is using some very sophisticated guess and check method, and they've come up with 3.09 as my power. Okay, which kind of makes sense because power 3 would give me 27. 27 times 2 gives me 54. So I will need a little bit bigger number than 27 here, which I get by 3.09. So let's go ahead and do the same thing with this one here. You can do it two ways. You can graph 5x in y1 and 100 in y2 and look for the intersection. I'm going to do it slightly differently. I'm just going to make it equal to 0. Okay, move the 100 to the other side of the equation, make it equal to 0. And I'm going to graph this, and I'm going to see what this graph looks like. And what I'm looking for when I graph this is I'm looking for the zeros. Okay, so I get 5 to the power x minus 100. And I'm just going to use, I need to expand my window a little bit. So I make my y min negative maybe 150. Okay, when I have that, I get a graph that looks like this. So I'll show you what my graph looks like. So my window that I used is from negative 10 to 10, negative 150 to 10. My graph looks like this. Here's my 100, that's my vertical shift. Okay, negative 100, so that's my asymptote. And it's going to go up very quickly like this, which exponential graphs do. And I'm going to calculate my zero. So if you're doing this on Desmos, you can probably just touch that spot. Okay, and here this intersection, the x value that makes this equation work is 2.86, and it's a really awful decimal just because it keeps on going and it never turns. This is an irrational number, so I'm going to just round it to 2.86 for now. So that was pretty close to my guess that I had here. We knew it was between 2.8 and 2.9, and we kind of just, and then settled with 2.85, so that's pretty good. So this is a bit more concise, and essentially we're just using better guessing, okay, and that helps us solve this. So this is, again, all in the context of an exponent, right? We're looking at this from an exponential perspective. We really still haven't answered the question of how do I undo that exponent? We kind of did here with, we kind of can undo exponents by making a common base, but we want to have a better method than that.